Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today I'm going to be giving you an introduction to cumulative distribution functions and probability density functions. We'll begin with a discussion of the cumulative distribution function. Cumulative distribution function. I will commonly denote it as a CDF. And you'll recall from our last video that the cumulative distribution function is denoted with a capital letter, subscripted with our random variable assignment as a function of the real numbers that the random variable can take on. And this equals the probability that my random variable is less than or equal to some real number. Especially when we're considering discrete random variables, that less than or equal sign will be very important. It'll be less important when we start talking about continuous random variables, but for the time being I'm going to try to be as meticulous as I can about my less than or equal signs. Alright, we're going to consider an example you should be quite familiar with. My chance experiment is going to be to toss two fair six-sided dice and observe the spots up. My sample space has 36 equally likely, 36 equally likely outcomes. Outcomes are going to be designated alpha sub I j, and designated in such a way that little I equals number of spots up on die 1 and j equals number of spots up on die 2. My random variable assignment is going to be the most common random variable assignment. That is I'm just going to add the spots up. That's what I'm going to do. Alright, as we've seen in the past, this is my random variable assignment table. When I toss two fair six-sided dice and add the number of spots up, I can get anywhere between 2 to 12 total spots up. I can't get less than 2, nor can I get greater than 12. Also, from our last video, over on the right-hand side of the screen is my probability mass distribution. This is my PMD probability mass distribution for my chance experiment when I toss two fair dice and then subsequently add the total number of spots up. So what I want to do now is calculate the values for several locations on my cumulative distribution function. Alright, so first of all, we'll notice that my cumulative distribution function evaluated at 1. Remember, cumulative distribution function is the probability of my random variable taking on a value less than or equal to 1 in this case. That also equals the this is the cumulative distribution function evaluated at 0, which equals the cumulative distribution function evaluated all the way down at minus infinity in all cases, that equals 0. It's not possible for me to toss two fair six-sided dice and get total number of spots up less than 2. My cumulative distribution function for all values, my cumulative distribution function equals 0 if x is less than 2. Notice I'm not saying less than or equal to, if it's less than 2. All right. What about my cumulative distribution function evaluated at 4? This is the probability that x is less than or equal to 4. Well, it includes that spot, and that spot. This is very clearly probability that x, probability that x equals 4 plus probability that x equals 3 plus probability that x equals 2, and altogether that's 6/36. All right, what about this? What is the cumulative distribution function evaluated at 11? Maybe I need to give myself a bit more room. What's my cumulative distribution function evaluated at 11? Well, that's going to include adding up all of these points up to right there. And that will clearly equal 35/36. The cumulative distribution function evaluated at 12 equals the cumulative distribution function evaluated at 14, which equals a cumulative distribution function evaluated all the way up to plus infinity, and that equals exactly 1. I add up all of these spots. All right. The probability that my random variable takes on a value less than 14 means to add up all of the probabilities lying to the left of that red vertical line. Okay? All right. So let me erase my marks here, and I'm going to do another example that at first might seem a little bit strange, but will allow me to draw out an important characteristic, important general characteristic of cumulative distribution functions. So bear with me just one second. Let me get all these marks erased off. All right. Let's do another example. What is the cumulative distribution function evaluated at 4? The cumulative distribution function evaluated at 4, that's the probability that x is less than or equal to 4. Clearly, we saw that that includes this point, and this point. This is 6/36 or 1/6. Now let me ask you this. What is the cumulative distribution function evaluated at 4.3? What's a cumulative distribution function evaluated at 4.3? 4.3 would be about maybe right there. The cumulative distribution function is the probability of lying to the left of that value. It remains, since I haven't gotten up, since I haven't gotten up to the point where I'm including 5 points, 5 spots up, my cumulative distribution function evaluated at 4.3 remains what it was at exactly 4. It remains 1/6. What about the cumulative distribution function evaluated at 4.7? That remains 1/6. What about the cumulative distribution function evaluated at 4.999? Still not including the probability that the sum of spots up equals 5. Well, that remains 1/6. Okay? All right. Remember, when we look at cumulative distribution function, this is the probability that x is less than or equal to little x. We look at the probability of lying less than or equal to x. Okay? All right. So, based upon this rather extended example now, let me write down the general properties of the cumulative distribution function. I hope that this will make some sense for you. So, general CDF properties. CDF CDF properties. These are general statements. These are true in general. 1. The limit as x approaches minus infinity of my cumulative distribution function equals exactly 0. Going back up here, my cumulative distribution function becomes 0 and stays 0 as we look at values less than 2. I'm sorry. Yes, that's correct. 2. The limit as x approaches positive infinity of my cumulative distribution function is exactly 1. All right? My cumulative distribution function always approaches 1 as the argument gets arbitrarily large. Third property, and this is the one that is sometimes a little bit confusing. Cumulative distribution functions are continuous from the right. Cumulative distribution functions are continuous from the right. That is if x naught is a point of discontinuity, if x naught is a point of discontinuity, then the limit as x approaches x naught from the right, that plus sign means from the right, or looking to the left. The cumulative distribution function evaluated at x as x approaches x naught from the right equals the cumulative distribution function evaluated at x naught. Okay? Next property. Cumulative distribution functions are always non-decreasing functions of their argument. All right? Cumulative distribution functions are always non-decreasing functions. They can plateau out. They can have some flat regions, and we'll see an example of that in just a few minutes. But they can never decrease. As you add more possible outcomes, you can't get less probability. The cumulative distribution function can never decrease as the argument increases. It can flatten out, it can plateau. The fifth property is that the probability that a random variable lies in the range x1 less than capital X less than or equal to x2 is evaluated this way. I take the cumulative distribution function evaluated at x2 and I subtract the cumulative distribution function evaluated at x1, and of course this equals the probability that x is less than or equal to x2, and I subtract the probability that x is less than or equal to x1. Okay? We'll come back to this fifth property in just a few minutes. I want to examine the first four properties by once again considering our toss two dice, observe the spots, create a random variable by adding the spots up example. So, going back to our same example, toss two dice, toss two fair dice, add the spots up. This is our probability mass distribution in the upper left-hand corner. And on the right-hand side is our cumulative distribution function. Now, once again, you'll notice that my vertical scale is multiplied by a factor of 36. And just to remind you that my vertical scale is the cumulative distribution function for x, I've reminded you at the top of the vertical axis that it's the probability that x is less than some specified level, little x. All right. So you'll see that my cumulative distribution function is 0. As I move towards negative infinity, it's 0% likely that my random variable is less than 2. There's a probability of being exactly 2, but there's no probability of it being less than 2. It's 100% likely that my random variable in this case will be less than or equal to 12. So as I move towards plus infinity, my cumulative distribution function approaches 1. You'll see that my cumulative distribution function is always a non-decreasing function of the argument. It does plateau, as we saw in the example just a few minutes ago, between 4 and 4.999999. My random variable stays the same. All right, we saw that before. It plateaus out. That's allowed, but it's an always non-decreasing function of its argument. Also, from the example that we saw just a few minutes ago, it's appropriate to come in and put square brackets and open limits, square limits, open limits. All right. What this means is that the cumulative distribution function is continuous from the right, looking to the left. All right. once we include that fifth spot, I move up here, have a soft boundary condition there, hard boundary there, soft boundary condition there, etc., etc., etc. So my CDF is continuous from the right or looking to the left. This particular point is something that students in the past have had some confusion with. If you have any concerns about this whatsoever, please do let me know, and let's talk about it. All right, so this is the cumulative distribution function for this particular random variable. You'll notice that it is a discrete random variable and involves several step functions. We'll get back to that in just a few minutes. Let's do an example to highlight the fifth property of CDFs. Once again, this is my, I'm considering my tossed 2 dice and add spots up. All right, that's my chance experiment. My random variable is that's really my random variable. Toss 2 dice, observe the spots, add the spots up. This is my random variable assignment table. That's the experiment that we're talking about. That's the random variable assignment that we're talking about. So let's examine that fifth property. Let me remind you that the fifth property says that the probability of the probability that my random variable lies in the range x1 to x2 inclusive of endpoint x2 but not including endpoint x1 is the cumulative distribution function evaluated at x2 minus the cumulative distribution function evaluated at x1. All right. What's the probability that my random variable lies between 4 and 7, exclusive of the endpoint 4 and inclusive of the endpoint 7? This is simply the cumulative distribution function evaluated at 7 minus the cumulative distribution function evaluated at 4. That's 21, 36 minus 6, 36. Or 15, 36. Now to get access to these values, you're going to have to probably go back and look at the probability mass distribution, the cumulative distribution function, and the random variable assignment tables. I'm going to leave it to you to go work that out on your own. Please do practice and check my math. What about this one? What about the probability that x lies between 4 and 7 inclusive of both endpoints? Hopefully you'll recognize that this is the cumulative distribution function evaluated at 7 minus the cumulative distribution function evaluated at 3. In this particular case, what we're doing is if we're including endpoint where the random variable assignment equals to 4, we're excluding everything else. That would be 3 and lower. This works out to be 21, 36 minus 3, 36, or that works out to be a half. All right. What about this one? What's the probability excuse me. Didn't mean to do that. What's the probability that my random variable lies between 4 and 5, inclusive of the endpoint 5 and exclusive of the endpoint 4? Clearly, this is the probability that x equals 5. This would be the cumulative distribution function evaluated at 5 minus the cumulative distribution function evaluated at 4. That's 1036 minus 636, and that works out to be 1/9. All right. What about this one? Probability that 4 is less than or equal to x is less than 5. All right. Well, this is really only the probability that x equals 4. This can be written as the probability that x equals the cumulative distribution function evaluated at 4 minus the cumulative distribution function evaluated at 3. And that works out to be 636 minus 336, or 1/12. Couple more. What is the probability that x is greater than 4? Greater than 4. This is also the probability that x lies between 4 and infinity, exclusive of the point 4. This is my cumulative distribution function evaluated at infinity minus my cumulative distribution function evaluated at 4, and that's clearly 1 minus 636. That works out to be 3036, or 15/18. And the last one for this particular series of examples, what's the probability that my random variable is greater than or equal to 4? Well, this is probability of 4 being less than or equal to x, less than or equal to infinity. This clearly excludes a random variable equaling 3, 2, or 1. So it's going to be cumulative distribution function evaluated at infinity minus the cumulative distribution function evaluated at 3. I'm going to throw away the probability of being less than or equal to 3 in this case. That's going to be 1 minus 336, and that works out to 33/36. Okay? So we've been spending a lot of time talking about particular chance experiment of tossing 2 fair dice and the associated random variable equal to the sum of spots up. But I don't want to leave you with the impression that all random variables are discrete. I can have continuous random variables. Here is an example of a continuous random variable plotted in the upper right hand corner of the screen. This is just a function I pulled out of the textbook. The cumulative distribution function shown in this curve can be written this way: 1/2 times 1 plus 2 over pi 2 over pi times the arctangent of x over 5. All right. You'll notice that my cumulative distribution function asymptotically approaches 0 at x equals minus infinity. It will asymptotically approach 1 as the argument approaches plus infinity. You'll notice that it is an always non-decreasing function of the argument, and it's true that this function is continuous in all cases, moving from the right to the left. However, since it's a continuous function and I have no points of discontinuity, that's a rather uninteresting fact. But it obeys all the proper properties. So let's calculate some values here. The cumulative distribution function evaluated at infinity is 1/2 times 1 plus 2 over pi times pi over 2. Clearly that equals 1. The cumulative distribution function evaluated at minus infinity is 1/2 times 1 plus 2 over pi times minus pi over 2. And that clearly equals 0. The cumulative distribution function evaluated at 0 is going to be 1/2. You can plug in the values. All right. Cumulative distribution function evaluated at 0 is clearly 1/2 due to the symmetry of this particular curve. The probability that x is less than or equal to 0 equals clearly 1/2. Okay? Okay. So enough about cumulative distribution functions. Let's spend a little bit of time talking about probability density functions. And I'm going to designate probability density functions as PDF. All right, let's talk about the properties for cumulative distribution functions. Excuse me, for probability density functions. The probability density function is designated with a lowercase letter, subscripted with the random variable designation, evaluated at the various real number values, little x. And this is the first derivative of my cumulative distribution function. All right, I find the PDF by taking the first derivative of the CDF. All right, so let's talk about some of the properties. One, since the cumulative distribution function is an always non-decreasing value of its argument, then the first derivative is always positive, meaning that the probability density function is always positive. All right? It's always positive. Probability density function is always a positive number. All right. Second property. If the probability density function is the first derivative of the cumulative distribution function, then I can find the cumulative distribution function by performing an indefinite integral of the PDF. In other words, the cumulative distribution function can be written as Alright, this is an indefinite integral, and I know some of you are going to take me to task on this, but according to the fundamental theorem of calculus, an indefinite integral has its lower limit, minus infinity, and its upper limit is indefinite. Alright, this is an indefinite integral. Indefinite integral. I suggest that you go and look at your first calculus book and look up the fundamental theorem of calculus. Look up the fundamental theorem of calculus. You'll find that indefinite integrals indeed have limits. It's from minus infinity up to x, although in most cases we just drop the limits when we're talking about an indefinite integral. So, as an example, let this be my probability density function for x, and let's let this point be a value x naught. If I integrate from minus infinity up to point x naught, I get this area. This area is the integral from minus infinity up to x naught. This is the cumulative distribution function evaluated at x naught. All right? I integrate from the left-hand side of my probability density function to get my cumulative distribution function value. All right. A corollary to my second property, let's call this property 2a, is that if I integrate from minus infinity up to plus infinity, this is my cumulative distribution function evaluated at plus infinity, and that's exactly 1. What that tells me is the area under a proper probability density function is always exactly 1. Area under all proper probability density functions is exactly 1. All right. There's yet a second corollary to my second property. Let's call this property 2b. What if I have this? What if my limits of my integral are x1 to x2? What if I integrate my probability density function between limits x1 and x2? Well, I can clearly split this up into integral from minus infinity to x2 over my probability density function, little f, and subtract from that integral from minus infinity up to x1. And this is my cumulative distribution function evaluated at x2 minus my cumulative distribution function evaluated at x1. And that in turn can be written as the probability that my random variable lies between x1 and x2. It's a probability of lying between limits x1 and x2, exclusive of the endpoint x1. Once again, if we, at the point where we're talking almost exclusively about continuous random variables, my less than or equals signs are going to be largely irrelevant. But I'm going to try to maintain less thans and equals as long as I can. So looking at this property 2b, if this is my probability density function, and this is point x1 and this is point x2, and I integrate my probability density function from point x1 to x2, this is the probability that my random variable lies between x1 and x2. All right. Over time, property 2b will probably be our most important and potentially most useful property. All right. So I'll put a big star on this and say that's an important thing to know. All right. A third property, more or less, is that discrete random variables can be expressed mathematically. Discrete, or rather PDFs for discrete random variables. Let's try that again. PDFs for discrete random variables can be expressed by recalling the following. The derivative, first derivative of a step function let me just write it down, then I'll dissect this for you slowly. The first derivative of a step function is a delta function. So let me remind you what a step function looks like. Step function looks like this. Step function looks something like that. It's 0 for x less than x naught. It's weighted by the amplitude a for values greater than x naught, and it's more or less undefined at the value x naught. My delta function then looks something like this. All right, that's a Dirac delta function. Hopefully you've seen that before. In this case, the value A is commonly referred to as the strength of my delta function. All right, so let's consider my cumulative distribution function for my toss 2 dice and add the spots up experiment. I'm going to write down that cumulative distribution function as a series of step functions, and then I'm going to take the derivative to find the probability density function. So let's use this property and come up with the probability density function for that particular random variable. And again, we're talking about the toss 2 dice and add spots up experiment. Toss 2 fair dice. My random variable is add the spots up. The cumulative distribution function for that random variable that I showed you just a second ago can be written as 1/36 times a whole bunch of step functions. Let's see if I can get them written down. U of x minus 2 plus 2u x minus 3 plus 3u x minus 4 plus 4u, excuse me, 4u x minus 5 plus, where am I? 5u x minus 6 plus 6u x minus 7 plus 5u x minus 8 plus 4u x minus 9 plus 3u x minus 10 plus, where am I? 2u x minus 11 plus u x minus 12. Okay? A bunch of step functions. All right. Very simply then, I can take the derivative of my cumulative distribution function and I get a bunch of delta functions weighted exactly the same as they are in the cumulative distribution function. My PDF for this experiment then is as follows. It's going to be delta x minus 2 plus 2 delta x minus 3 plus 3 delta x minus 4 plus 4 delta x minus 5 plus 5 delta x minus 6 plus 6 delta x minus 7 plus 5 delta x minus 8 plus 4 delta x minus 9 plus 3 delta x minus 10 plus 2 delta x minus 11 plus 1 delta x minus 12. Whew. Whole lot of writing. Bunch of delta functions. My cumulative distribution function is a bunch of step functions, and my probability density function for this particular experiment and random variable assignment is a bunch of delta functions. If I plot my probability density function, I get that. This is the probability density function for the random variable equal to the sum of spots up when 2 fair 6-sided dice are tossed. There you go. That's a bunch of delta functions. This is not equal to the probability mass distribution. This is not the same All right, it looks a whole lot like the probability mass distribution. The probability mass distribution was a bunch of dots at more or less the same location where the arrows on these delta functions end. However, delta functions are true functions. They're functions in the truest sense of the word. The probability mass distribution is just a plot of probability. It could also be expressed in tabular form in a table. look similar in this particular case, but they are not equal. Please give some thought to that and let me know if you have any questions. And once again, you'll notice that the vertical scale has been multiplied by a factor of 36. This point is really 136, and that point right there is really 636 or 1/6. Okay? Please give some thought to all of that. That's all I have for you for today. As usual, if you have any questions, please let me know at your earliest convenience, and I'll get back to you and answer all questions as fully as I am able. Have a nice day. Bye-bye.